Let's start the small signal modeling of PNP transistor. Remember, we did the same thing for the NPN transistor, right? So this is the pi model, right? Base to emitter junction is replaced by a resistance because of the small voltages, small signals, small AC signals, right? So, and the voltage across this R pi is V pi or VBE, right? And collector current is equal to GM VBE, right? And GM you already know, IC over VT. The we have derived the relationship and draw the curves, and this is the early effect resistance R naught, right? And if you have something at the emitter, it is recommended to use emitter T model instead of pi model, right? So this is the T model for an NPN transistor. How about PNP, right? Because P is emitter is at the highest voltage, then base, then collector, right? So it will be looking like this one, just vertically flipped up, right? Then your current is from emitter to collector, right? This arrow is showing this. Here it was collector to emitter, same arrow, right? So now you have from emitter to collector, same arrow, emitter to collector, and remaining things are same. You have an R pi resistance between base and emitter or emitter and base, same thing here. You have R naught from emitter to collector, same way here. So now you are ready to connect your other resistances if you have in your amplifier for PNP transistor, right? How about the T model? It would be also be the same. Emitter, RE, this base. So you have a resistance between base and emitter, but in T model, that resistance is explicitly at the emitter side, not at the base side. Whereas in pi model, emitter base, there would be a in between emitter and base, there would be a resistance, but explicitly it would be at the base, right? Consider this amplifier. This amplifier has been configured in which configuration, right? Can you say something? You can see you have your input applied at the base and your output is collected at the collector. So this is a common emitter amplifier for PNP transistor. Don't be confused by this supply, because in there collector is at the highest voltage, emitter is at the lowest voltage. You have DC supply here, but grounded terminal. Here in PNP you have DC supply, but a positive terminal. So don't be confused with this one. So this is a common emitter amplifier based on PNP transistor with an emitter resistance, because emitter resistance is not bypassed here, right? So this is a common emitter amplifier. How about this one? Is emitter resistance is bypassed. So this is simple common emitter amplifier, not with emitter resistance, right? Because emitter resistance is bypassed, right? So in AC equivalent circuit, you have a short ground here. No emitter resistance would be present. How about this one? You are applying your input at the base, you are collecting your output at the emitter. So it means your collector is common. So this is a common collector amplifier. So please try to do all these things, find their relations of AV and GV yourself. Just consider the things I make you clear with the polarities, right? Everything else would be the same. But still, I want to give you an example of this one, the common collector, because usually it looks difficult, right? Consider this problem statement in which you have been given the already given the Q point, R1, RC, and RE. You have to find the R2 here. Don't worry, we can find it. We have to draw the AC equivalent circuit by neglecting the effect of internal capacitance. You have not studied these things, and of course it is asked you to neglect it, so forget it. You have to draw the AC equivalent circuit. Write the expression of what? V in with respect to V signal. V out with respect to V in, AV and GV. Obviously, we write the V in terms of V signal to get GV, and V out in respect to V in to get V in, AV, right? And then use these things to find AV and GV, right? It means it it is asking you to use early effect for what? For obtaining the AV and GV. So it means here it says neglect the internal capacitance, not neglect the early effect, right? So let's do it. I solved it on the paper, question paper, so I want to show you here. To find R2, let's consider these things, that if this amplifier is in active region, even it is a common collector amplifier, but in active, this emitter base junction would be forward bias, right? So if this emitter base junction is forward bias, you have VEB is equal to 0.7, right? And you are giving what? You have been given the value of collector current, collector to emitter voltage, emitter resistance, collector resistance, and R1, right? So if I want to find the voltage here, it's very simple. 15 minus the voltage across this resistance will be the voltage here at the emitter, right? So what is the voltage across here? IERE, right? So 15 minus IERE is equal to VE, right? So I have IC, so I just divide IC by alpha to get IE, right? So 15 minus IC by alpha into RE is the voltage here. When I put the values of IC and alpha, beta is given, you can find alpha easily, right? So here it would be 10 volts. So if this transistor is in active mode, your emitter to base voltage will be 0.7. So if this is 10, this is 0.7, so it means this is 0.7 less than this. So it means 10 minus 0.7 is 9.3 here, right? So we have 9.3 here, 9.3, right? VE minus VEB is 9.3. But if you want to find this VB from this junction, if you neglect base current, you already learned that the voltage would be here because of R2. So you have a voltage divider from VEE to R1 and R2. So it means R2 divided by R1 plus R2 into VEE is VB, right? You can write this equation. VB is equal to R2 divided by R1 plus R2 into 15 VEE, and VB you already found from here 9.3. So put it here. R1 is given. Find R2. R2 is found to be 8.3 kilo ohm, right? So this first part has been done. So draw an AC equivalent circuit, right? So for AC equivalent circuit, you can make your DC supplies as grounded, voltage supplies grounded, capacitor as short circuited, right? So it means you have something at the emitter. Actually, your load is at the emitter, so it is recommended to use T model. So let's draw the T model. I draw the T model: collector, base, emitter, internal resistance between emitter and base, but explicitly at the emitter, current source at the base and base collector side, and current direction is from emitter to collector because of the PNP transistor, right? Then connect what? Collector to ground, because this would be short circuited. So collector is grounded, okay? At the base you have R1 and R2 in parallel, so you can write RB because parallel combination of R1 and R2 is RB. That's why they found it here. So RB, and then R signal and V signal, R signal and V signal. How about the emitter? You have RE to ground, you have RL to ground, RE to ground and RL to ground. And for early effect, you have to put from emitter to collector and internal resistance, the early effect resistance R0, right? So here you can see from emitter you have three resistances grounded. R0 is grounded, RE is grounded, and RL is grounded. So all these three resistances are coming in parallel, right? So now what we have to do? We have drawn this thing, find RE, find GM, right? Find R naught, then your this part will be done, AC equivalent circuit, right? Here I have drawn R naught here, and R naught would be found somewhere. Yes, GM here, RE here, R naught. You can do it yourself. Yes, here, right? So it means this part has been completed. How about this one? Write the expression of V in with respect to V signal and AV and GV and V out, right? So as you had been doing in NPN transistor for common collector configuration, same will be the case here. What about RIB? If you want to, because input at the base, you want to see internal resistances of the transistor at the base. So R input at the base, it looks to be small RE in series with parallel combination of these three things, right? But 1 plus beta time, because these resistances are at the emitter, so you want to see from the base. So Re plus parallel combination of these three resistances into 1 plus beta, right? This is RL prime, Re parallel to RL, parallel to R naught basically, right? So your RB is this one. So RIB is this one. How about Rn? So Rn is equal to RB parallel to RIB, RIB, RLD form, right? So what about Vin? Vin will be equal to Rn divided by Rn plus R signal into V signal. Vin is Rn divided by Rn plus R signal into V signal. What about Rn? Rn is Rv parallel to RIB. RIB already found, right? Please put R naught here. So this is done for this one. How about V out? Since this V in, the found V in will be across this resistance Rin and its parallel resistance Rib, right? And Rib has further divided into two resistances, two series resistances, right? This one and this one. It means Rin is divided into this resistance and the parallel combination of these three resistance. So it means V out is nothing but the voltage divider biasing between this three parallel resistances and these Re, right? So it means V out will be equal to R naught parallel to Re parallel to RL divided by Re plus all these three things into V in will be equal to V out, right? And if you bring this down, you will get AV. How about GV? So instead of bring it down, you can put V in relation this to bring this V signal here, right? So in this way you can find Rin divided by Rn plus R signal into this old relation. So you can put AV instant. So this is your GV relation. Now if you put VA this one, right, to get the R naught and other things, you will get the values of, by putting all these values here to get 0.968. You know, your AV is nearly 1, right, in common collector configuration, and your GV is less than AV, but it depends on your R signal and R in, right? So this is all about PNP transistor. Please do other configuration yourself. Whole PNP transistor will, all the things we have studied for NPN transistor will be included in the terminal examination. Now we have two lectures remaining, very simple one, because if you understood the NPN transistor, you will understand the N channel MOSFET. If you understood the PNP transistor, you will understand the the P channel MOSFET, right? And all the configuration are same. Instead, in fact, it is simple. MOSFET would be simple than BJTs, right? So it is not late, because I want to make you understand everything with this one. Usually in the class, I use the same route. Only few lectures are enough for MOSFET if I put more effort and I train students more towards the BJTs. So thank you very much. And this would be your homework 7, not to be submitted, but please do this thing on the copy, simulate it to verify, right? I made the simulations, but I don't want to show you here. Please do it yourself. Thank you very much.